Okay, welcome everyone to the September 5 iQuiz seminar. It's my great pleasure to introduce today's speaker. That's Philippe Bouyer. He's at the University of Amsterdam and the Technical University of Eindhoven in the Netherlands. He's also the coordinator of the quantum sensing program at Quantum Delta in the Netherlands. And he's the former deputy director of the Institut d'Optique and founding director of the Laboratory of Photonics at the University of Bordeaux. He has won his PhD, maybe I should say that at least. His PhD is from the École Normale Supérieure in Paris Sud. And then he was a visiting professor at Stanford. And now he's in the Netherlands, as we heard. He has received many awards. He is an APS fellow, and he is also the recipient of the Louis Grand Prix of the French Academy. So it's my pleasure to have such a high-profile speaker here at the university. And Philippe will talk about quantum sensors based on matter waves. So please join me in welcoming Philippe, and then we're going to listen to his talk.
Well, thank you very much for the introduction and for the invitation. It's a pleasure to be here. It's my first time in Urbana-Champaign, although I heard a lot about the great work, especially that Brian did. We were competing together at some point under some localization. That's a good thing. And so I will not speak about that, but I think I turned it on. Down this one? So that's the one. Okay. Fine tuning. Yeah, so I speak about matter waves, especially how you can use matter waves, cold atom-based matter waves to do inertial sensing. And oops. Okay. Okay. So this is actually a special year today, or this year, like 2023. It's exactly 100 years ago that Will de Broglie actually published his famous paper about wave-particle duality for matter and introducing the de Broglie wavelengths. So that's the concept that matter can actually behave like wave to a certain extent, and especially if you have a low velocity and a low mass. In that case, the de Broglie wavelength is very large. So even though that was a theoretical concept, the first demonstration happened very fast. If you look at electron diffraction experiments in the 30s, that's already basically a manifestation of the wave behavior of electrons in that case. But we had to wait until typically the mid-century to see the first actual manipulation and matter wave interferometers using light particles, electrons and neutrons. And basically, if you think about the neutrons, that's also the first patent that you can find about using matter wave sensors for measuring things, especially measuring rotation and gravitational acceleration. So if I invite you to look at those papers, if you think about the neutron interferometer, it is a very tiny thing. It's about that big. It's a crystal. It's a monolithic crystal with 3 slices in which the neutrons are diffracted. So it could be actually quite practical as a device that you can use for applications, although the source unit for a neutron is a little bit big. It's basically a nuclear power plant. So that was not completely useful. And we had to wait basically to some other revolution, in particular the invention of the laser at about the same time. And then the manipulation of atoms with laser or laser cooling in the 90s, and then the atom laser or Bose-Einstein condensate in 2000. To really see like a potential for those sensors to really be applied for practical solutions. And practical means applications that I will talk about, but also to develop fundamental physics aspect or explore like general relativity or things like that. And if you look now, I think if you look back in the 90s, you had some pioneering groups working on that, maybe less than in the palm of my hand. Nowadays, you have more than 100 groups working in that field on various aspects from application to basic concepts. So it's really, I think it's still a very growing and expanding field of quantum technologies. I will not speak about everything in quantum sensing, but I will focus on matter wave interferometry that is basically using cold atoms. So we cool down atoms to temperature of the order of microkelvin or less. So the velocity, the typical velocity of the particle is of like a few centimeters per second. We use laser cooling for that. Then these atoms, we will select the one that we want to use. So we select the proper velocity and we select the proper internal states, basically, and we launch this atom through a series of 3 light pulses. These light pulses can be Raman beams, 2 different frequencies, or Bragg beams in the same frequency. That's basically building a standing wave that will diffract, reflect, and diffract again the matter wave. So it basically creates a coherent superposition of 2 parts of the same wave packets flying away from each other with a velocity, a relative velocity, which is typically a photon recoil. So that's a few centimeters per second. And then we change the velocity, and then when they recombine, then we mix again. So we have 2 paths that the quantum system can choose to evolve. And of course, if you want to look at the probability for the systems to enter the interferometer and exit the interferometer in a certain state, then you have to compute basically the interference pattern between those 2 quantum paths. So how that, so far it's a nice experiment, and it's a nice, maybe even Gedanken experiment, but how can we call that basically a quantum sensor? And in the particular case I will address today, how can we call that an inertial quantum sensor? So how does it actually measure inertial quantities? Well, you can go back to quantum physics and you can say, okay, I have like my quantum system, that's my atomic system. I have to say in most experiments today, it's a single atom quantum system. So there is no multi-particle states involved in that. And then I create my superposition. I have these 2 potential paths, then they recombine again, and I have to compute basically the amplitude for the systems to evolve from the initial states to the final states. I can use path integrals, Feynman path integrals. So I have, in this case, to compute what is the amplitude for one path, what is the amplitude over the second path. Then I have to sum the amplitude. This is where I get my interference pattern. And to compute this amplitude, basically, what happens is I have basically to compute what is the phase, what phase is accumulating along each path. That's the Feynman path integral. So I can compute the trajectory of like the classical trajectory. The center of mass of my wave packets is following. Then I can compute the effect of a force or the effect of an inertial field to this path. This translates into a phase. And this is exactly what I showed here. This is this integral of action that you can find in the paper. This is one example of a paper for this calculation. And basically, if I do that, taking into account that my atoms, they have a mass. So for instance, if I want to do the experiment as it is like this, I have my laser vertical. My atoms are falling down because of gravity. So I have a parabolic trajectory because my atoms are falling down. I compute the phase and I find 0. So okay, so that's the end of my talk. Sorry for that, but no. So why is that? So one easy like handshaking explanation is all the effect, all the action was already taken into account to the modification of the trajectory. And this parabolic trajectory, I recall you, it's a geodetic trajectory, which is actually minimizing the effect, minimizing the phase effect on the system. So that's not surprising that you find 0, but then how can you measure something? There is something I did not take into account during this this calculation is the fact that the atoms interact with the light. And when they interact with light, they exchange energy. That's why you have the change of state. They exchange momentum. That's why the 2 wave packets are actually flying apart from each other. But they also exchange phase. If there is a phase corresponding to a certain position of the center of the wave packet in the light field, this phase is also transferred to the wave packet that has been affected by the photon exchange, by the interaction. So this phase comes to this term, exponential IKZ, and that's basically a phase that corresponds to the position of the wave packet here, there, and there. So I can change a little bit this picture, and I can go to the picture of an atomic gravimeter. I have this 3 light pulses. Then in more details, usually we make a standing wave, either with 2 or 1 frequency. The standing wave, we make it by having a mirror. That's easier because then you control the phase very easily. The atoms are falling down. So the trajectories of the 2 wave packets and the 2 center of mass of the wave packets are following this geodetic trajectory, this parabolic trajectory. At each time I shine the light, there is a position of the center of mass of the wave packet associated. Here I can take the average of the 2 wave packets that are separated. This is the midpoint theorem that you can hear about in certain publications nowadays. And from that, you do the calculation, you find out, and this is exact at first order, that the phase at the output of my atom interferometer is exactly corresponding to the distance the wave packet or the atoms travel from the first pulse to the last pulse, divided by my phase quantity, my phase definition, which is basically the laser wavelength in this case, and that's how many ripples of phase I have in my light field. So this is a GT squared, or 1/2 of GT squared divided by lambda, and this is the scale factor of my matter wave interferometer. This is a scale factor of my matter wave gravimeter in that case. As I told you, this is exact at first order. You'll see some more complicated equation in the next transparencies, but it tells you a lot about the matter wave interferometer. It tells you a lot about its properties, why it is so interesting, and what are the tricks that we will have to take care of in order to make it work. So why is it so nice? It's so nice because the scale factor for any sensor, the scale factor is what converts the quantity you want to measure in the quantity you're looking at. So it's either the needle change on your voltmeter, or it's a number that you have on your computer. And the scale factor is 2 pi over lambda times t squared. T is defined, is extremely well known with atomic clocks, up to 10 to the minus 18. Laser wavelength is extremely well known as well. You have laser metrology that gives you also the 10 to the minus 18 if you want. So this scale factor, you know it exactly. And you know it's not changing. And this is a number, this is a definition that you have from your system that you don't need to calibrate. You just need to measure. You just need to know what you're doing there. And the other thing that's interesting with that is because it relies on the fact that this ruler is very stable. If you try to measure something where you're shaking, it's not. It means that if you want to make it work, you will need to have a certain control about how it shakes. And that's basically because you are measuring the relative acceleration in that case between the atoms that are a perfectly free-falling mass. Atoms are under vacuum, they are not affected or barely by any other external forces, and the light which is used for the measurement. But if you put some numbers on that, then you say, okay, I know the scale factor very well. So if I want to measure a quantity, what I need to do is to measure a fringe like this. This is an actual measurement. Each point corresponds to a run of an atom interferometer with about 10 to the 6 atoms per shot. In that case, it's less than 10 to the 6 because the signal to noise is not that good. But so then you have, like, in order to make the measurement, you need to know on which, where you are on the fringe. And in order to do that, you need to have a certain signal to noise ratio. In that case, it's more like, it's closer to 6 or 10 than it is to 1000. But you can go down to, let's say, 1000 in principle. Then you can apply your interferometer with a splitting between the pulses of about a second. And if you do that, then the minimum acceleration you can detect, or the change in that case of gravity, a gravitational acceleration would be of the order of 10 to the minus 10 meters per second squared. That's about 3 to 4 orders of magnitude smaller than the amplitude of variation of gravity because of the tides. You know, the tides and the fact that you have the Earth going, the sea going up and down, or the Earth also breathing because you have like some tidal forces from the moon attraction, or like moon-Earth attraction, or the Earth-Sun attraction. So this is actually extremely precise. If you convert that into the gravity gradient of the Earth, that tells you that you are able to detect a change of height of less than a millimeter at this level. This would be the most precise height measurement. Up to now, if you want to measure height very precisely, you can use GPS in a very fancy way, and you can go in a two-way GPS down to a centimeter or thing. The best clock at a level of 10 to the minus 18 is also at about a centimeter, and this is much better. Of course, you need to reach that number, but if you reach that, it's much better. Okay, so just before telling you about applications, since we are in an institute of quantum technology, everybody speaks about the quantum advantage. So it's always nice to quote about the quantum advantage of our sensors. Why are they good for? So I told you before, we have a scale factor that we know extremely well. Because we know this scale factor extremely well, because we can actually also know from the physics of our system what are the potential bias of the measurement. We have an extremely good trueness or accuracy, which means that what we measure is exactly what we want to measure. What we get is what we are supposed to get. In other words, that means that when you shoot, you're always, on average, really shooting at the center of your target. But as I showed you before, on the other hand, we are also extremely precise, which means that when we shoot, basically all the points are recovered together. And the quantum advantage of our sensor is they are both at the same time. They are both true or accurate and precise. And it's important because if you talk to the clock people, or if you talk to any kind of metrology people and you tell them, I have a sensor and super precise. Then you look at you and say, what does it mean? It means that it's both sensitive and accurate, or it means that it's only accurate and not sensitive, so in our case, it's basically all at once. It's accurate, it's sensitive, and the thing is also, if you make a measurement over very long interrogation times, it will not drift, which means that it will always stay there. It will not have, on average, a drift that you need to compensate for. So that's why we were so interested in looking at applications for those sensors. And the first natural application, the most obvious, is the one I explained just recently, is the fact that you can take your cold atoms. They are so cold that they're falling down, and you can actually watch them falling down. It's time of flight measurement. And then you can use that to measure gravity extremely precisely with your atom interferometer. So we did that. And we did that exactly the way I mentioned before. So we have the atoms, we make the first pulse. Let's say the atoms at their initial position, and then they fall down. So after the second pulse, they are at 1/2 of GT squared. And after the third pulse, they are 2 GT squared, because each time it's a T that is between the pulses. Very nice. I am using now a coherent manipulation of my atoms. So it's a coherent interaction between atoms and light. If I have a coherent interaction between atom and light, basically the frequency, the relative frequency between the atoms transition, in the atomic transition, even if it's a 2-photon transition, and the light will be important. If my atoms are moving, there will be a Doppler shift, which means that I can be resonant here. So I can have a very good, let's say, diffraction pulse efficiency. But then at the second pulse or the third pulse, if I wait for a second, for instance, my atom will go at centimeters per second, even meters per second. And then it's sure that it's not going to work. So my interferometer can only work if I am basically changing the resonant frequency each time I'm doing a pulse in order to compensate for the Doppler shift. If I do that, that means that I add a frequency term into the frequency difference. And this frequency term will have to basically be compensated, for instance, by chirping the frequency of my laser. That's easy. I know at which rate my atoms are falling down. I know that I'm making a pulse every whatever seconds or 100 milliseconds. So I can just chirp the frequency so that at each time of the pulse, the frequency is exactly the one I expect. And because this is compensating the Doppler effect, and because I have an acceleration, so it's a linear modification of the velocity, this is just a linear chirp. So that's a very easy way to compensate for the Doppler shift. Of course, if I do that, it's like if I'm now measuring very precisely while I'm moving my ruler at the same time. So I have to take that into account into the calculation of the phase shift of my atom interferometer. And what happens is when I do the same calculation as I did before, but I did not show you, it's that the phase shift at the output of my interferometer is now proportional to kgt squared. So this is the 2 pi over lambda, g times t squared, exactly the same term as before, minus the chirp rate, alpha, times t squared. So there is a term coming from the chirp, which scales exactly as the phase term from the acceleration. It's not really surprising because I'm compensating basically for the acceleration. And that's very interesting because now it shows that I can just chirp like this, and I can chirp for different times. And then there is one point in which the output of my interferometer is always the same, or there is one point where the phase is exactly 0, and it is only the point where alpha exactly compensates for kg, for k times g, for the acceleration times the wave vector of the light. And this is basically how we measure gravity with the matter wave interferometer. We do not actually measure fringes. We chirp the light frequency, and then we apply it for different times, for example, a couple of times. And then I have a number out of my system. And this number is just the chirp rate divided by the laser wave vector. And this gives me directly G. So the measurement is done by a number, by just how fast I am chirping basically my laser frequency. Okay, so that's important that you remember that, because I will in some transparency explain how we don't do that in practice for our measurement now, but this is actually mostly what you do when you want to measure gravity. So knowing that, then we basically built a gravimeter, and we not only built it, but we patented some nice idea in order to simplify it, and then we are able basically to build a commercial version of our gravimeter. So this is my company, my former company actually, which was called Nuquants, and I recently sold it last year, and now it became a bigger, like much bigger company, Excel. And these are 3 of the 14 gravimeters that we have sold so far all over the world. So in this, you have the atoms that are cooled down in a pyramid trap, and then they fall down, and because of the property, the optical property of the pyramid, when they are out of the pyramid, then you have just a mirror here that is reflecting the light and is making these Raman beams that I mentioned before. We can then measure gravity very precisely in this, and then you have the laser system and the electronics in this big box over there. And the level of this gravimeter is actually among the best. I mean, this is the state-of-the-art measurement of gravity you can get nowadays. It is beating the existing systems, which are superconducting gravimeters. Those ones can be a little bit more sensitive, but then in order to make them work, you need to calibrate because you don't know, and they don't drift that much, but you need to calibrate, so you cannot move them because as soon as you move it, then you need to recalibrate. And the other one is a falling corner cube, so it's really like the atoms. But you let the corner cube here fall down. You measure it with laser interferometry. But of course, if you make a piece of glass fall down, then you have mechanical vibrations and etc. So in that case, you don't have those problems, and you can record gravity. So these are the tides. You have some kind of bit knot structure because you have 2 tides frequency, and the one which is the Earth-Moon gravity and the one which is the Earth-Sun gravity, and they don't have exactly the same periodicity. So that's why you have this bit knot. And this is just to show you that you can record that in days. I mean, this is a few days, even many months. And what's also interesting is the residuals from that. So the residuals are the order of a microgal, which is 10 to the minus 9 G. It's not limited by the instrument. It's basically limited by the knowledge of the gravitational noise and environment that we have. Remember that 10 to the minus 9 is less than a centimeter of fluctuation of height. So anything can actually be noise in that case. But it's so sensitive that in order to get this line almost flat, not only do you need to take into account the tides like this, but you also need to take into account something that we call the ocean loading. So the fact that because the Earth is going up and down, it's changing basically its pressure on the tectonic plate. So the tectonic plate is actually changing height by a few centimeters, and you need to take that into account in order to actually have an accurate model of it, just to tell you how sensitive it is. Yeah, the atoms. And yes. So no atoms has been harmed in this experiment, as you say. So you know what happens on the atoms in a vacuum chamber. At some point, they stick to the wall, and then they are basically, because it's a vapor equilibrium, then they eventually go back from the wall after some time, not so often. And we operate at very low pressure. I mean, it's the vacuum pressure is 10 to the minus 9 millibar, or even less than that. And the atomic pressure is maybe 10 to the minus 7 millibar. So we have like not so many atoms in there. So it does not really affect the system. And we recollect some atoms. Whether they are the same or not, we don't really care. I mean, as long as we have some, it's fine. But yeah. So most of our customers, they are geophysics labs, or like like USGS, or so geophysics lab or geophysics institution that are doing some gravity. We don't have so many. Well, okay, when we started the company 10 years ago, we thought that there was a big market on oil and gas. Maybe there is still, but oil and gas is a market very hard to attract, and you know the fluctuation of oil and gas. So it's but we're still also discussing with oil and gas in some way. But so for now, I mean, I will give you 2 examples of applications where the geophysicists are very interested, but it has an impact beyond actually the geophysics community in some way. For example, this one. So this is a collaboration with some French laboratories of geophysics, and they want to use gravimetry in order to understand what is the cycle of water. So how much of the rain is actually stored into our underground reservoir. And this is a very complex story. I mean, this is because most of the rain drops on the surface, and then the tiny slice here, which is called the epicarp, so it's very tiny. But this is not actually retaining so much water because there are lots of evaporation there. So this is not very efficient for your water reserves. What you want is ideally, you want the confined groundwater reserves that are very deep. And then you have a very slow diffusion process that depends on the material, the soil, and everything. And they want to understand that in order to understand well, how to manage our water reserves. And you can do that with gravity. And this is, I think, one of the first gravitational measurement of basically the loading. So this is the model in which you see you have the rain, then the rain is actually charging your massif, and then you can actually, and this is just the change of density because you have some water into your like porous soil, and then this is the recording from our gravimeter, and it shows that. And that's the first experiment. And ideally now what we want is to also have, for example, eventually a gravimeter there and look at the gradient and how they evolve and etc. So this is a type of study that is being done, but it already tells you a lot about this, what it can provide. If you have, for that, you need not only the sensitivity, but you need the long-term stability because, okay, you need to wait for the rain and then you need to wait for a very slow diffusion process and etc. The other interesting thing, it's a consortium with also geophysicists, but now they want to use gravity as an early monitoring of like catastrophe, in that case, eruptions, volcanic eruptions. In that case, what you want is to be able to monitor the magma mass coming at the bottom of a volcano. And then if you see a big mass coming, it might be an extremely good indicator about the risk of eruption and etc. And you can predict that. And so if I show those pictures, you don't understand anything, neither do I. But if you believe the geophysicists and they make the comparison, this is actually a sign that you have some magma mass, some bump of magma mass at some point. And this corresponds to something like many, like thousands of tons of magma, but 4 kilometers below the Earth, below the top of the mountain. So that's the geophysicists who are good. We are just very proud that we were able to put a gravimeter at the top of a mountain in Vietnam, and it's been running there for more than a year now. And of course, it has not been running continuously, and this is not because of the gravimeter. This is because of the eruptions at Vietnam, a few eruptions. So there are a few cases where we cannot run the things. You still need electrical power, and during the winter, you rely on a power, like a power generator. And if there's no fuel, then nobody can go. So then you just have to wait for someone to go up. And then the system has to stop. Then someone comes, starts it again, and it works. And then you can measure, like after half an hour, you measure gravity as if you never stopped measuring it. Yeah. Yeah, exactly. Yeah. Which corresponds to ridiculous amount. I mean, this is a change of nanometer per second squared. So it's like 10 to minus 9 G typically, or something like that. No, it's okay. So there is no independent measurement because you cannot measure this. What they do is so this is why. So you have the gravimetric, which gives you an absolute measurement, and then they have also they have other type of, they have electromagnetic measurements. So it's a multi-parameter measurement. As any sensing experiment, you need many parameters. So you can compare that with electromagnetic perturbations and also some other accelerometers that give you some local information that you can extract from in order to get the deep gravity measurement. So this is not so easy way of measuring it, but you don't have, I mean, you have to rely on the measurement because you cannot go down and look at the magma. This is not possible. So this is typically a case where you need this like this gravimetric measurement to do it. Okay, so that's two examples I wanted to give you of some applications and some like concrete applications that we are currently doing with these quantum sensors. There are many potential things. I talked already about gravimetry, but one other aspect of gravimetry is to make a map of gravity map and look at anomalies, and that can actually allow you to look at buried resources on the ground by just looking at the difference. Again, you need models and you need all these kind of things, but you can do that very accurately. I will speak about the applications to GPS-free navigation because I think this is an important one. And then, of course, there are lots of aspects in which you can push the sensitivity of your sensor in order to go to much more sensitivity, and then you can actually test new models of physics, new gravity, like models related to general relativity. You can test the equivalence principle. You can try to detect gravitational waves. I won't have time to talk about that, but there are many projects, even in Fermilab, there is a similar project here, in order to like build some gigantic interferometers that will beat the sensitivity of anything else in the world. But let me focus on one aspect, which is position, navigation, and timing. Here, the challenge is to use our precision and accuracy to actually compensate for the fact that you might not have access to GPS all the time. So how do you compute your position today? So of course you can use your watch and your GPS, but even in your watch or even in your iPhone, you always have some inertial navigation system that give you some quick, some fast, high data rate information. So basically that relies on your ability to measure your internal acceleration vector, so the modulus and the attitude. And then from that, you integrate twice and you get your position. And that works really well. I mean, we even have an inertial navigation system in our body, and that's actually working fairly well. Even though if I close my eyes and I want to reach the door, there is no way I can do it. And this is because even if we have a fairly good system, and even your iPhone has a fairly good system, you might reach the door with the iPhone, but eventually it drifts. You have an unknown bias in the sense that the bias is actually a noise of the system. You don't really know it. You can calibrate it, but then because it drifts, you know it at one time and you don't know it later. And if you integrate twice like a bias, then it leads to an enormous error in positioning. Nowadays, the best inertial navigation systems that you would find in some military submarines, for instance, they have some accuracy of the order of a few tens of meters per hour. I mean, this is the best you can get. It's more like 100 meters per hour. And even in a plane, if you don't have a GPS, then or like some site, you won't find your airport if you're crossing the Atlantic or something like that. So that's a challenge. And that's a challenge that because we are bias-free with our sensors, we might be able to solve. And there are actually two possible approaches today in order to solve the problem of GPS-denied environments for navigation. One, and this is the example for gravimetry, but you can also use it for magnetic mapping with NV centers, for instance, is to rely on a map of anomalies. Let's say you have a very precise map on gravimetric anomalies or magnetic anomalies, and it's been proven that those anomalies are pretty unique. I mean, you can have unique points on the Earth surface, which will just describe that point with respect to the magnetic or the gravimetric anomaly you are looking at. And the level for gravity is of the order 10 to minus 7G. So it's at reach with our systems. So this is an example. So in that case, for example, if you want to sail and you want to be free of GPS, you could have a gravimeter on board your boat or the plane. And this is an example here of a gravimeter that is being mounted on board, in that case, a helicopter. This is from Onera in France. So they just took a gravimeter like the one I showed before. They put it on like a super fancy gimbal that is actually compensating for all the pitch and roll of the boat or the plane. And then you can measure gravity with that. And this is some measurement done with a gravimeter. And the idea is really to have this map and then to use our knowledge for gravity. Let's say you navigate with your inertial navigation system. And at some point, you look at your map. You recalibrate your position with respect to your anomaly detection, and then you can go on by navigating with that. This is very good. And recently, I think the US Air Force has done some demonstration on that with like F-16 with an NV center lagging 10 meters away from the F-16. But you need a map, which means that if you want to fly over a certain place where we cannot fly anymore, I can tell you, I was trying to fly from Korea to Europe, and there is only a tiny place where you can fly. Then all the other places, you cannot have the maps. And you will not be able to have the map because you can rely on satellite. But if you have a satellite gravimetry, it's not going to be good enough in order to have the details of your map. You need to fly fairly low to get even magnetic or gravity maps good enough for that. So then what you need to do is to really go back to what you know. Is, okay, can I measure acceleration in my mobile environment in a way that actually my gravimeter or my accelerometer in general is actually feeling what my plane, my boat is doing. So let's go back to the gravimeter. So this is again an example of the gravimeter I showed before. So this is where the atoms are. This is all the electronics and optics and etc. And then I told you it's very nice. I have my laser and I have my atoms falling down, and then I have my mirror. I compensate, I chirp the frequency because I compensate for gravity. But that works because I know that I'm measuring gravity. That works because I know that I'm measuring along the vertical direction. So you need to rely on this gimbal in order to do this. If now I want to measure an arbitrary acceleration in an arbitrary direction, which is what I want to measure if I want to navigate with my system, I cannot really just chirp because I don't know what I will chirp, in which the quantity of it. So just to give you some schematic, usually what we do in order to get this gravity is we have this quantum accelerometer, then we can rely on the measurement with a classical accelerometer. I'll come back on that in the next transparency. And then I have some information about the environment, and I can remove that, and then I get a measurement of G, which is basically a very low rate measurement that is integration of my quantum sensor. Now I want to apply it in a real moving environment. And this is an example of the experiment that we've been operating in this specific plane. It's a plane that is also reproducing microgravity situation. I think here you call it the vomit comet. And I confirm this is sometimes the case. And so what's interesting with that plane is it gives you access to microgravity, but it's also a real environment. It's a real plane. I mean, it has the noise and it has the rotation rate and etc. Plus it's fun. You see, it's some of my collaborators and students, and we do the experiment in microgravity, and this is something pretty unique. If you're not sick, but just out of, I think, 10 students that were working on that program over the years, only one was sick. But then he couldn't see a plane for another month because, okay, so I'm in the plane. And these are basically the data I get from the plane. The black dots are when the plane is flying still, and the green dots are when the plane is actually doing the parabola. There are a few bias, but don't worry about that. But the first thing you see is then where are my fringes? I don't really have fringes. So what I do here is I repeat my experiment. I have a duty cycle of typically like 10. So it's like every 100 milliseconds, I cool down my atoms, I do my interferometer, I have a point. I cool down my atoms, I do my interferometer, I have a point. The result is a random distribution of points. Then you would say, okay, how can you actually get any information out of noise? Because that's basically what we have here. Well, the first thing you can look at is at the distribution, the statistical distribution of these points. And if you look at that, it's a pretty regular curve. I mean, we call that a Batman because it has the 2 ears there. And the ears are super important. This curve is exactly the same as you would have if you take this nice sinusoidal distribution with a certain signal-to-noise ratio and a certain contrast. And actually, the size of the ears, that's the signal-to-noise ratio of your interferometer. And the distance between the ears is the contrast. That means that all the information you need to know, you need to retrieve, is buried in those points. So the only question is, how can I get them? So I recall to you that we know the scale factor very well. So we know actually the position of the fringe here. We know exactly to which acceleration it corresponds. We know the contrast. We know the signal-to-noise ratio. So we know everything about our sensor. We just don't know on which fringe it is. And that's the problem here, is because the acceleration is so large that basically we are like flying over many, many fringes, and that we have no way to reconstruct the fringe in an easy way. So how can we do that? Well, something I did not mention, but if you calculate also, if you do the math of your matter wave interferometer, there is another quantity or another aspect that you know very well. It's the transverse function of your sensor. So we know exactly what the sensor is doing to a non-static acceleration. At a certain frequency, it will have a certain response. So now we just need to record the noise, in our case, the acceleration of the mirror. And then from that, we can just actually integrate into the transfer function here the effect of the classical acceleration. And this is how basically we retrieve the measurement of our quantum sensor from a noisy environment. And basically, even on the commercial gravimeter I showed before, we do that. I mean, we have a sensor on the top of the the thing so that we don't need to put it on a specific platform. And we are limited at 10 to the minus 9G because of the environment. But up to this, we can have vibrations and we take care of it with our hybrid approach here. And this was the first time we were basically able to pinpoint for a certain time the acceleration of our plane with a quantum sensor. So that was very interesting, but that's not enough to make a measurement of like to use that for navigation. First, because you don't have enough points. So that everything that happens between here and there, if you don't know what it is, it can be an error in your position. So we need to go beyond that. And in order to go beyond that, we need to build like a specific device, and we need now to take into account everything that happens to our sensor, not only the vibrations, but also the rotations eventually. So we put so this is a prototype of a quantum navigation system, like an accelerometer and everything. I'll come back on that. And we put that on this platform where we can simulate rotations and tilts and everything. And then we found out that you have two problems that you have to cope with in addition to vibrations. The first one is the fact that if I just put that in a static way, let's say I now want to measure the acceleration along one axis, my laser in this direction, but it's tilted like that, then I need to know what is the acceleration in order to compensate for the Doppler effect. And if it's not like this, but this, I need to compensate, and etc. So I need to have some active compensation in order to be able to keep the contrast of my interferometer good for all type of orientations. I show you that we can solve that, but then, and it's just a teasing about the other problem that we have to solve, is now if it's rotating like that, then for instance, let's say I want to measure gravity, and then I'm rotating like this, the same thing I do in the plane. Then I have two wave packets that are flying apart from each other in a rotating frame like this, which means that I will have a Coriolis acceleration that is actually pulling my wave packets apart from each other, but in the perpendicular direction from the plane. In other words, I can make a nice interferometer this way, but if I look in the other way, I'm not making an interferometer because I'm not closing my interferometer. And you all know that if you make an interferometer and you're not closing the interferometer, eventually you lose contrast, depending on the comparison between the distance of the opening of your interferometer and the coherent length of your systems. So this is exactly what will happen here. If we are not coherent enough, then eventually we won't be able to measure anything because we don't close our interferometer. And there is nothing you can do with that. There's nothing, really, you cannot do anything. I mean, it will be pulled away from each other. Yeah. Okay, so we need to compensate for tilt and rotation. And this is just to give you some example of the measurement of the effect of this pulling apart. I mean, you have a lot of contrast. You can calculate it very precisely. Again, the good thing with our sensor is we can calculate everything. We know what's happening. And then this is, for example, 1G is when the plane is still, 0G is when the plane is rotating at a rate of 90 degrees in 20 seconds. And rubidium and potassium, that's two experiments that we had in the plane. Temperature here were of the order of like 3 microkelvin, here 10 microkelvin. And you see that you lose contrast very fast, only a matter of a few milliseconds of interrogation time. That's just because then the splitting between the two exits of your interferometer is larger than basically the coherent length. So this is actually a measurement of the de Broglie wavelength or the de Broglie coherent length in that case. Okay, so we need to solve all this, and then the way to do it is a little bit more complex than what I showed before. So now we need not only to know about acceleration, but we need to know about attitude, and we need to know about rotation rate. So we need basically a classical navigation unit, accelerations and rotation, so fiber optic gyros and mechanical accelerometers. This is our continuous output. This will actually measure the attitude of our mobile or our vehicle at a very high rate, as any system is doing. And then from that, we have information about the rotation rate of the system and information about the acceleration. And eventually, there is a bias because our node system is not perfect. But then all these informations, we plug it into our manipulation of our quantum sensor now. So this is like a picture of the 3 pulses, you know, the first, the second. And so usually I would chirp this if I was measuring gravity, but now at each pulse, I will actually apply a certain phase shift or frequency shift that corresponds to the acceleration, the change of velocity that I can imply from the knowledge of the relative movement between my atoms and the mobile. So that sounds very simple in this way, but this is actually not that simple, because in that case, you really need to go very deep into the model of your quantum sensor, because you need to take into account the fact that the pulse, the light pulse, is not like infinitely small. So there is a certain area of the pulse, and so it depends on the time you apply the change and etc. But again, this is just quantum mechanics. You can calculate it very precisely, and you know exactly what you're doing there. Just to be clever enough not to do it in a stupid way, but usually you learn it the hard way, but we learned it and it works. And then it works in the sense that now it's a measurement where I am at different time, I am measuring. So it's a static measurement, this one. I have my accelerometer, and then I'm rotating it. And this is Z axis, so which means that I'm starting from Z, and then I'm going into the horizontal direction like this. And as you see, I keep a high contrast. Of course, it drops here because I'm horizontal. So then in that case, my atoms are just like falling down and I'm not measuring anything. And this is y-axis. So this is measuring from the horizontal to vertical. And you see this dip, which is, okay, if I have just one arm, then I can only measure along one direction. Of course, then, okay. And so now I want to look at what's happening in a dynamical way. So now I have a rotation. And again, I will not make some precise calculation, but you can compute what is the effect of what is the inertial phase coming out from an acceleration and a tilt and a rotation. And this gives you this very nice formula, in which you have basically our accelerometer, what we call, is measuring any kind of acceleration, like any accelerometer. It's also measuring Coriolis acceleration. It's also measuring centrifugal acceleration. So all these terms are relative to the relative velocity between the atoms and the vehicle. So the geodetic trajectory, the atoms and the vehicle, their relative acceleration, and etc. And this is a fairly complex thing. Again, I do the measurement. I have this stupid distribution of points, but for each point, I can actually correlate that with acceleration, but also with tilt and angular velocity. And if I plug all those numbers into this, I get this nice curve here, which here you see it's corrected phase. That doesn't mean anything, but that's because it allows all these terms there. But it's just to show you that an accelerometer is also not such a bad gyro, is that basically if you fix the tilt, because we know the tilt, then you reproduce a nice fringes. It's a rotation measurement now from the accelerometer we have, simply because you have this rotation term into the system. So the interesting thing from that is that here I don't have my nice Batman curve like the 2 ears, and that's simply because this curve is actually, you know, it's like at high phase here, it's actually dumping out. It's dumping out because I have a contrast effect, because I'm rotating at high rotation rate. I will lose contrast, and this is exactly what happens on the edges, and this is why I don't have this nice curve. So the first thing I can do, because I know what my sensor is doing again, I can post-correct this from the knowledge of the contrast loss, and not surprisingly, I reconstruct exactly the fringe I expected there, and I reconstruct the statistic, which is telling me, okay, I'm doing a good job, but I have not solved my problem, you see. I just know that I don't know that I understand my problem fairly well, but I have not solved it in the sense that here at large rotation rate, you know, the density of point is very poor, simply because I don't have a very good signal to noise ratio, because the contrast is super minimal. And so in the last couple of minutes, I will introduce how we try to correct that, and it's only a few slides. So it's, and that's okay. In order to solve that, we can go back to what I showed before. We can put our big machines into a big gimbal like this that is rotating and compensating for other movements. But I don't need to do that, because basically what happens with this effect is my atoms are free falling. So they're following a geodetic trajectory. Let's say I'm in my parabolic flight like this, and then at some point I cool down my atoms, then I turn off all my lasers, and then my atoms are following a parabolic trajectory. And then the only thing that happens in my laser is actually not following exactly this trajectory, because I have additional rotation. And this is what is actually doing this effect. So if now I compensate on the movement of the laser and not the whole vacuum chamber while I'm doing the measurement, then I can compensate from the Coriolis acceleration. So this is exactly what we do here. We put our mirror, which is doing the standing wave, on a tip tilt mirror on which we have the acceleration measurement of the mirror, and then we have rotation measurement with the fogs. So this is a whole hybrid integrated systems. And then when the system is rotating, when I pulse for like 10 microseconds the light, then I'm also rotating the laser while I pulse. Then I turn off the light. I don't do anything. I don't care. Then I turn on again. I rotate the laser again. So I introduce a rotation of my mirror to compensate for the rotation. So it's like, let's say in some way, the light is always following like this while the system is rotating, but it's not quite like this because I do it only when I turn on the light. And that works very well. Again, I can do the full calculation, and it's a little bit more complex because now I have to take into account the Coriolis acceleration, the centrifugal acceleration, and then I have the relative Coriolis and centrifugal acceleration that corresponds to the differential rotation between the actual trajectory and the mirror. So that's why I have all those terms, but again, I can calculate it. So no big deal. And there's no, I mean, at the end, I just have velocities, time, there is a distance somewhere, which is a little bit tricky. That's the distance between the mirror and the atoms. So there are a few quantities that I need to know, but it's not that hard. I mean, it's not like I have like a full model with like complicated software to do in order to model like a mechanical system, for instance. And with that, I can actually compensate for the contrast. And oops, sorry. I lost one. No, this is the one. And this is exactly what happens. Now this is no compensation. So you see the contrast falling down for light. And when I compensate, then I have no loss of contrast. So now my accelerometer is basically working all the time. And just to show you that it works very well, I will not extend. So we extended it in 3D, but it's just like 3 times the same accelerometer. So we do it one this way, one this way, one this way. So in that case, we basically built an actual navigation system, which is a hybrid. It has fiber optic gyros, classical accelerometers, and then we recalibrate this classical navigation unit with the knowledge of the accelerometer from our 3-axis accelerometer. And this is what's happening there. This is the curve that I want to show for my conclusion. So what's on this curve? The purple curve is the output of our classical navigation systems. So that's the acceleration measurement from our classical systems. And as you see, it works very well here at short term. But then at some point, you start to have bias, uncertainty, drifts, and then you cannot integrate anymore. This is a classical Allen variance of a very bad system. And so that means that after, like for this system, after a few seconds of integration, then you cannot gain in position knowledge anymore. Actually, it's even worse, you lose in position knowledge. And now what you see, and this gap is just technical, is at some point, the quantum system catches up again and actually compensate from the drift of the classical accelerometers. And then you can still keep on integrating. So this is to tell you that we have this kind of internal recalibration system. We don't rely on an external GPS that tells us, oh, the quantum measurement tells you this. The classical system has drifted, so you need to compensate for it. And this is what we've done here, the classical Kalman type of integration for data fusion, and showing that we can actually use our quantum advantage in order to get a very good navigation. And I will stop on that. I thank you very much for your attention.
Great. Thanks, Philippe, for a very nice talk. Are there any questions? Students first? Postdocs second? I see you, Elizabeth. I'm still waiting. Students, anyone? Okay, here we go.
The y-axis on this graph here, that's just the Allen deviation. So this is basically the noise, the Allen deviation, in terms of gravity. So this is 10 to the minus 4g. This is 10 to the minus 7g.
There's one over there.
So there is no power during that time. Well, that was one of the uncertainty that we tested. So while we try to have a system that is mostly relying on, gators and ion pumps. So I guess the vacuum went up while the current was gone, but not like sufficiently good enough in a way that when we turned it on again, then the ion catched up again, and we went down to the proper thing. But yes, that was a test. It worked.
Okay. Anyone else? Yes, go ahead. Do we start with the condensate, or is it a thermal gas?
So that's an excellent question. So we cool down our atoms, but we don't cool them down at the degenerate temperature. So it's typically a few microkelvin. Why is that? It's well, at this level you need to have a trade-off. So of course, let's say we don't use all the atoms we cool down. Let's say we make a MOT and we have like a billion atoms, and we use only less than 1 million of those because we make a very harsh like velocity selection. That would eventually be better with the BEC, but it takes much longer. I mean, we want to have a high duty cycle. So I mean, it's a trade-off between the complexity of the system and why you would use it. For instance, if I want to make the experiment in space, then I will need a condensate, but I don't really care to have a duty cycle of like a millisecond. I can have seconds. So that's really and if someone can make a BEC in like half a millisecond, then we can do it.
All right, so I think I'm officially moving on to Elizabeth now.
Yeah. Presumably, except that we try to be in a magnetically insensitive state in order not to be sensitive to magnetic forces. Yeah. Yeah, I think it's true that in most cases we try to be insensitive to anything. We even sometimes have magnetic shield around to be, but well, okay, this can be a very good magnetometer in a way. It will measure the magnetic. I'm not sure it will measure the magnetic gradient. It will measure the magnetic force that applies. So even a constant magnetic field will have an effect on that case.
Okay, so I think we'll move on to lunch at this point. Please make sure to not forget your lunch ticket, I believe, and join Philippe for lunch. But before that, please join me in thanking him again for